There's nothing like going as the last talk of the day right before happy hour, so my apologies for that part. I did want to introduce this briefly and say that I wish it were a light talk here at the end of the day, but it isn't, so bear with me. Hopefully you'll find it interesting. This is brand new work, and a set of colleagues and I have been very involved in this for the last year, but this is in fact the first time we've talked publicly about the details of how we're doing this and our thoughts in this particular topic. So the title of my talk is Making the Internet Video-Centric via Decentralized Content Fabric. And I just wanted to open the discussion by raising the question, did you ever wish we could rebuild the internet for video? And specifically, if we think about it, today the internet is no longer a network of data, it is now a network of content. Cisco projects that 82% of the bytes that flow over the internet within 3 years will be video. And of course, live video is growing the fastest proportionally of all types. So I'd like to explain a little bit about how we got here to the current internet architecture and why we might need to rethink this and how we might go about rethinking this for video, and then get into some of the details about this notion of a decentralized content fabric. So obviously the internet began as IP routing. In the beginning, it was for routing data between hosts, and interestingly, that model by itself was always decentralized. You can add a router to the internet, it knows how to route IP, and no router needs to consult with any shared state in any centralized form in order to know how to extend that routing protocol. Also note that thanks to TLS and SSL, the data flows over that routable network in a trustless fashion. However, as the internet matured and our applications grew on top of it, our uses became largely a client-server architecture, and those are largely centralized. So much so that all of our data and our content ended up in servers, databases, and now cloud object stores. And in order to lighten the burden, improving the throughput, trying to get content off of the core, we deployed edge caches en masse. And today we largely have an edge cache-based model for serving video content in this ever-growing scale to consumers around the world. And yet, and I want to use a quote from a very famous paper by Van Jacobson, who's one of the authors of TCP congestion control and really a father of the modern internet. Van said in his paper, Networking Name Content, which was really now almost 10 years old. His paper was written in 2009, that a single packet in a typical YouTube stream would traverse the link between youtube.com and the user's ISP over 1 million times. And Van was introducing a brand new paradigm, and in fact, I got to hear that talk when he first talked about this in 2006, when he was still at Xerox PARC. His talk was titled Content-Centric Networking, and frankly, I've been thinking about this idea ever since that talk. Van's idea was really an academic initiative to replace IP with content protocols, and the main driver for this was to reduce or completely to remove this redundant core bandwidth usage that had become consequent with the growth of all the content that goes over the internet. Now, obviously, it's impractical to replace the internet routers. There's also no intrinsic tie in that model to the value of the bytes saved or to the improved quality to incentivize the change. It missed the rest of the stack. There's a lot more going on than just routing, and it's very difficult to achieve at large scale. So consequently, content-centric networking has really been, up to this point, an academic initiative. We feel in our group, though, that arguably now it's potentially possible and also necessary, given the scale of video over the internet, if we're really going to have breakthroughs in how we get content to users. And why is that? Well, first of all, we have large-scale AI and machine learning that makes it practical to solve network optimization problems that we couldn't solve before. GPUs, CPUs, and TPUs are now the inexpensive resource compared to bandwidth and storage, which allow us to not only solve those large-scale ML problems efficiently, but also to do just-in-time serving of media. And then with the maturation of decentralized ledgers, otherwise known as blockchain decentralized ledgers and trustless security, it is now possible to think of a truly trustless fabric architecture where you can have large-scale consensus. Valuable media can move through third-party nodes, if you will, third-party systems in a trustless manner. And you can also have open pricing, which incentivizes participation. So this creates, we feel, is a unique opportunity to think differently and to apply these content networking principles to create a new software overlay for the internet that is decentralized and that is programmable. The goal with this is to take a simple and elegant approach, hopefully in a single software stack, and to do it in such a way that's truly scalable and allows for end-to-end content protection on a platform that self-grows, meaning it has to be trustless, and also that has intrinsic commerce at scale, just like we had commerce at scale with search in order to incentivize participation. So great vision, but then of course the technology. How do you actually make something like this happen? And this is what I want to dedicate my time to for the rest of this talk. There's a lot of technology that needs to exist in this, and I first want to talk about the principles and then specifically the key areas of technology that we've worked on and go through the details of those. So first is we want to take an internet overlay approach, meaning we're not going to rip and replace any of the internet as it is, and we want to harness the platforms and capabilities that are there. We can, however, make an intelligent software stack that can be deployed uniformly in a distributed and decentralized manner where state is not shared and instead coordination is through an open protocol. Content and metadata need to be stored in an efficient way in this so that the output variants can be rendered from single source. We're no longer creating these umpteen million variants in file-based form and pushing them through the network and the storage over and over again. The delivery needs to be low latency and high performance, as we've heard all day, otherwise it won't get used. And that needs to be true even as the network grows. The content nodes cannot be trusted, but the content itself also needs to be protected. However, in that process, we need a way to incentivize the right kind of behavior. Access control need be mediated through the most advanced technology that we have, and that is, in fact, through decentralized ledgers. That does not necessarily mean that we have to turn media into a cryptocurrency-backed commodity. It does, however, mean that we can take advantage of decentralized consensus in the blockchain model and also smart contracting to help to back the integrity of media and to have tamper-free transactions, and also to be able to create open marketplaces with high scale in commerce. And then last is we need to have programmability in this so we can have flexible media composition, and a conference like this underscores this in every capacity. So with that, getting to the specifics of the technology, I'm going to focus on the 2 red bullet points in my talk today because I don't have time to cover all 5, but all 5 of these elements go together to make this possible. First and foremost is this content storage model. How do we go about achieving scale and speed and minimal duplication in the content as it is in the software fabric? Second, how do we achieve low latency, high performance content routing and delivery? Just-in-time composition of media, binary content, and the code that's used to make it is fundamental to serving in this way. And then finally, how do we achieve a trustless security model with blockchain-controlled content access and fast, provable content version history, which is also entangled directly with the blockchain-controlled content access. So with focus today, I'm going to start with the content storage model as some introduction, and then I'm going to talk about in detail the content routing system and also the just-in-time composition pipeline and show you some of the performance numbers and some of the open issues. So first off, for content in the fabric, I'm going to get a little water here. My mouth is dry. Okay, so in this model, we want to think of media and digital content in its most natural form, which is raw binary content metadata that describes it, and code, if you will, that can be used to render it. And all of that is stored in a uniform way as chunks of bytes, blobs, on nodes that run the Content Fabric software. And then there is a well-defined semantic inside the fabric that allows those to be structured so that the hashes of those parts can be reused across multiple objects that derive from the same parts. And you'll see how this fits together so nicely with the way that we generate and consume media. And then those are composed together at the time of access or consumption, which allows for great reuse. It also allows for personalization. Each object is backed by a blockchain transaction, and that records its version change history and also gives a way to have a cryptographic proof of its parts so that we can have tamper-free versioning once and for all. And the integrity of the object can be verified by any clients that read from the fabric through a fast proof calculation. And just taking a look at this visually, you can see a very simple diagram in the upper right. If we think of each of those parts as the binary blobs, that includes the metadata itself, the binary media, and any code. Those then are referred to through a content object structure, which can refer directly to the raw parts as well as the metadata, and those roll up into a top-level content reference. And all of this is comprised of, or is represented through hashes, and those hashes and their structure together constitute the fingerprint of this particular object and its version. And then if we look at the user request pipeline, you can see as we're going to generate an output rendering, we can simply operate code, which is part of that content structure, on the raw media and the metadata itself in order to compose and serve whatever variant that the user wants at that particular time or that the application calls for. Now, as we're thinking about this decomposed model then, we can start to take this into a distributed structure. And one of the most important parts is how do we partition this across a network so that we can achieve true scale? And I want to mention that this historically started with peer-to-peer networks. The distributed hash table is a large-scale structure that started almost 20 years ago, and there have been many attempts to do this in peer-to-peer systems. The typical downfall is that as the number of nodes or the number of objects in a DHT system grows, it either becomes too slow to locate parts, or parts have to be, or the content that's being referenced has to be moved around, or both. And as a result, we've never seen a large-scale peer-to-peer system serving broadcast quality video that has grown and stuck at scale. So in this case, we have invented a novel DHT structure, and it has a couple of key properties. The first is the ability to locate parts fast with low latency. And in our world, low latency is we fill under 500 milliseconds, even as the number of nodes and the number of content objects grows. And it also avoids reshuffling as the network grows. And I'll show you an example of this in a moment. One of the basic ideas of this is that in any point in time, the network has a level and it has a number of partitions per node. And these can be changed over time to allow the network to dynamically repartition, and that's calculated through an open protocol that all the nodes know. And in the process of repartitioning, content does not move around. In fact, it's able to be easily shed at very infrequent periods. The nodes determine their partitions by their ID, and content parts will then flow to these partitions based on a prefix in their hash. And the length of that prefix is increased as the number of nodes in the network grows. And then parts are assigned to the nodes based on a calculation that's easy to do fast through an XOR distance algorithm. And let me just show you an example. So imagine that we have a part that starts with 0F1A, if we have a hexadecimal representation. So at level 3, let's say the network's at level 3, and we have a node that shares those first 3 hexadecimal characters, 0F1. So of course at level 3, that part will be on that node. As our network repartitions and gets bigger through level 4, it continues to stay on that node because the XOR distance is still at 0. Now let's imagine that the network gets even bigger at level 5, and we're now comparing the number, an XOR distance with the 5th hexadecimal characters, 6 and 0. Now we're at the point where our XOR distance is equal to a value 6, and if the current configuration of number of partitions is 6 or greater, the part will stay on that node. And then finally, as we move to a level 6 network, then the part and the nodes assigned partitions diverge. The node sheds that particular partition containing that part. How much did the network grow throughout that process? It grew 16 raised to the power of 3, or 4,096 times in size before we had to move that part. I want to talk a little bit about content routing around this partitioning scheme. So it's very important in this fabric concept to be able to achieve low latency routing and also to be able to select preferred routes. So I want to talk a little bit about the routing architecture and then our continuous machine learning that allows us to select the best paths based on nodes that will serve with good bandwidth and also low time to first byte. So most importantly, in terms of routing, to find these parts, we consider working inside of a domain and then working between domains. And the intra-domain protocol is really quite straightforward. We can take advantage of the fact that local broadcast and even IPv6-based multicast is available, whether we use it or not, on computers today. So a local domain lookup is as simple as broadcasting out to or multicasting out to all of my peers. Do you, in fact, carry the partition for this part? If they do, they respond back, and we've already satisfied the request. Now, if we need to go outside of our local domain in order to find a part, we can also do that with a lightweight and fast routing lookup. And in that particular case, each of the nodes keeps a very lightweight interdomain routing tree. And notice that each node learns the IP address of various partitions, and if a node doesn't currently know that, it can go up simply one level in the tree, and then the node that it's going to can repeat that process looking inside its domain, making that broadcast. If it gets a response, that IP is learned, and the part is served from that upstream node. Now, when we do this, it's all fine and good, but imagine what if we choose a path, a particular route, or we choose a particular node that is poorly performing. It doesn't have the bandwidth, or it's not going to be able to meet the latency target that we're after. So we spent a lot of time building a continuous machine learning system that allows us to do overlay routing, where we can, in fact, minimize startup latency, maximize the delivery bandwidth, and also minimize the core bandwidth usage to keep the cost as low as possible. And in our model, we consider our overlay to be served by, let's start at the bottom, a client to an egress node. That's a path we don't control. An egress node host computer with constrained bandwidth and capacity, an origin to egress segment, where if we don't have the part on the egress, we go back to the origin, and then finally an origin node with a constrained bandwidth and capacity. And if you look at the routing algorithm, it's very likely that we can find parts within at most 2 hops. So this works very well in tandem with the routing model. So in this continuous learning model, what we do is we record the delivery bandwidth and time to first byte attributable to the egress origin segment and the egress nodes. We score the segments and the nodes to train, and we use this train model to identify the best segments to route the requests. And then we developed a collaborative filtering algorithm, actually a few of them, that are applied independently on the egress nodes and the overlay segments in order to select the best routes. And then we train this continuously and fast in our network. Now, because this is such an elaborate system, first we wrote a simulator to test our models, and in that we modeled what would be the canonical topologies for an overlay network that goes across an unknown internet core, and wrote a simulation that would allow us to start many clients and allow them to traverse these topologies and test the selected routes. And after we were satisfied with that, we decided to then implement this and test this in the fabric in the real world. We have run the fabric software in these tests I'm going to show you on 52 nodes in a public cloud network. And we're looking for a few things out of this. We want to see that the routing trains the clients to choose sensible routes with high bandwidth, low time to first byte, and also good locality, because that saves on core internet bandwidth use. So I decided to pick out a few we mapped our results on Google Maps. So you could see the width of the red lines, or the amount of bandwidth that was used by the clients, and of course the topology is the endpoints. So you can see the North America clients after training, obviously before training went all over the world, after training stayed exactly where they're supposed to stay. Same thing in selecting egress nodes. Instead of going all over to all egress nodes, they chose precisely the North American or US-based egress nodes. Same thing with the European clients, untrained versus trained, and these are even hard to see because they're yellow. And then same thing with the egress nodes that were selected by those European clients. Another view on the same data is to actually look at a scatter plot of the client bandwidth after training across each of these continents. And you can see here blue is the trained values, and all of those are at least 5 times what they were in the untrained case. And then also the time to first byte is very important, because in a moment you'll see that this is what lets us guarantee our time to first segment at a very low latency. And same thing if we look in the upstream egress to origin segment, very good bandwidth after training and very low time to first byte. And then I'll slow down on this slide because this is important. That red line is 500 milliseconds. We measured the time to first segment, not time to first byte, but time to first video segment. And this includes the video segment at the client, the download time, right? And you can see across each of these continents, red line is 500 milliseconds. Meet that everywhere. We didn't meet it in Asia. It goes, it's at 1 second here up to about 1.4 seconds total. And that's because some of the Asia clients have to go out of region. We didn't have enough nodes to serve them there. And that gets to these pricing incentive models. In a case like this, raise the price incentive to get more nodes into that region, right? One other piece of ML that we use extensively here, we built some predictive caching models using machine learning. We obviously don't rely on caching as our main efficiency gain in this network, but we do use it opportunistically. And we had some training data from one of the Hollywood studios, provided some screening data for the last year, 12,000 some titles, viewers in 120 countries. And we were able to train our caching models there and get very nice results out of that. One of the blue is our predictive caching. And one of the nice things about the just-in-time model I'm going to show in a minute is the fact that we can cache and train based on titles only. We don't have to worry about output variance. So I know I don't have a lot of time left, but I do want to spend some time on the just-in-time composition concepts within this and what we've learned for video. Obviously, most of us in our team are network people, so we're no experts in video, but what we're trying to do is make a fabric that supports the expertise that people like you have in video. And so if you think about this kind of a pipeline idea where you can render just in time using the availability of compute and the personalization that comes from that, we have an opportunity with modern software elements to do just-in-time composition. And we do this in the fabric using LLVM, which is a set of compiler tools that compile code into an intermediate representation. And that representation can be built on the fly, and it gives us a nice way to create a sandboxed environment for I/O of content and metadata with the fabric, and a security sandbox, as well as metering to do pricing incentives for composition. And we use this in many ways in the fabric. One way that we've specifically exploited it is to transcode directly from source packages such as IMF sources to Dash and HLS on demand. And the way that we built that, for example, is when we publish IMF packages into the fabric, bitcodes creates the parts and populates all of the IMF CPL data into metadata. And then when a user comes to stream, another piece of bitcode actually composes the Dash manifest and the segments on the fly from that instructional material stored in the content objects. And it's a very powerful way because we don't have to generate any of the package segments or any of the Dash packages ahead of time, and it gives an enormous amount of flexibility as well as efficiency to the pipeline. Now, I want to take a little bit of time on this slide because it's very interesting, I think, to a video community to see what you can really do if you pay attention to a pipelined environment like this. And this is the blow-by-blow dissection of a segment's journey as it's being served and transcoded through this kind of a pipeline in our fabric. So first and foremost, if you want to get a little orientation, the red is compute time, the black is network travel, blue is transcode time, and then our playback is actually shown in green. And what happens if you remember this overlay concept is that you have a client that's getting this request for content that comes to node A, and that node may have to go to another node B to get that part. Node B sends that part, and it arrives to node A. And note that the first segment is actually pre-transcoded, and then node A is sending that, piping it straight through to the client over the network, and all of this takes place in less than 500 milliseconds. And at the same time, that egress node is also transcoding the subsequent segments and transmitting the transcoded content out to the client in a pipeline manner. And the goal, of course, is to get every segment to the client before the time of playback needs to start. And if we do this effectively, right, we actually made a heat map of the arrival time of segments at the player relative to the playback time. If this is good, we should see that we always come in under the very dark blue 4-second values for 4-second segments. What you see here are 7 different dash segments, 3 different clients, and we did 16 different videos. We actually generated these as a mezzanine track from the Meridian IMF package. And note that these are 4K H.264, 25 megabit per second, 4-second segments, so very, very high bandwidth, because the goal is to do this for very high quality. And I'm not going to say very much about the security model because I don't have time today, but it does support this very importantly. And if you don't know about trustless models, I would encourage you to learn, because it gives us, if we can really get trustless security done, it becomes possible to create a platform that can self-scale, grow beyond the size of our current internet clouds. It also gives us a way to make media provable, and that's a very exciting concept in this world where it's difficult to verify the origin of content and whether it is in fact correct. There's this notion in blockchains of smart contracts, and we use them extensively and transparently inside of the fabric. We have a built-in blockchain ledger. This isn't going against a public blockchain. It isn't using a token for tokenization, but we do this in order to make the access control around the media transactional so that it's possible to do interesting things between users and content owners and sponsors that will incentivize participation in such an environment. And I just pulled out, if you haven't played around with blockchain ledgers, it's really interesting to look at. Our core blockchain is, of course, conforms to the Ethereum virtual machine interface. It is a custom stack because we've also had to do some work there to get the blockchain to scale. And if you have questions about that, I'm happy to answer. And then finally, I've talked about this, but each of the content objects carries with it a version proof, which is a fast proof mechanism composed over the part hashes. And this is really important because it means when clients read out objects, they can quickly verify that they've read the version the fabric claims to be sending them. And then this also becomes a mechanism for being able, at a user interface level, to advertise whether something is in fact a verifiable version and to tie it back to the version history in the blockchain itself. So I just want to wrap up by showing you a little bit about this. I'm just going to play some content through the fabric that's generated directly or streamed directly off of IMF, and I'll show you a couple of transactions that are happening around it. So just to, and I know I've gone over time, so I'm not going to update. Thank you, iTerm. But just want to show you a little bit. So this is an IMF package that I just published into the fabric. And I'll just give you a little look at that. Here, you can see the IDs of the assets and the individual names of those assets taken from the IMF. We populate a few of our own fields. Those are going to be used in the smart contract itself. We generate some offerings, and these are encoded JSON values. And then, notice here, these are the actual parts, or at least the hashes of those parts, for the individual XML and JSON files, as well as for the tracks themselves. For example, this is the English video master track. This is a title crawl that you'll see in a couple of different languages in a moment, right? And then the other thing I just wanted to point out was to publish this, and all I did was run a CLI command to publish into the fabric. The bitcode runs to generate these, and of course we can do things like dynamically apply watermarks. That can also be done on output, you name it. So I'm just going to pull up a demonstration app that we created. We call it Continuum in order to demo this a little bit. And I'll just use this particular version of Star Wars here. So I'm going to go ahead and play that. First, I have the English version. Maybe the guys will turn up the audio so you can hear a little bit. Guys in the back, can you? There you go. And notice this is playing directly off of that IMF source, okay? So we didn't pre-generate any of the segments or any of the dash manifests. And if I move over here to the Japanese version, right, that's going to generate the Japanese version with the right Japanese title crawl. I'll just let it go to the title crawl so you guys can see that. There we go. And then just one more thing, I wanted to show one little bit of commerce around this. So I'm going to go ahead and play one of these guys that is powered by an ad. So let's see here. There we go. So notice, watch this user's account, which is currently 511.36. When I get to the end of this ad, this credit is going to go up by 1 value. And that's a smart contract running on the finalize of this access. See that? And the value is programmatically set in the contract. Then it's going to go down by 2 when I start the premium content because the charge for for playing this is in another content contract is set for a value of 2. And this doesn't have to be actual money. These are just virtual value between accounts. I'll just bring up a standard Ethereum wallet so you guys can see this real quick. So here we go. Here was one of my earlier events, paid the client credit. This is the client's address, the Alice blockchain account, and then finally that credit amount. It's in a power of 10 to the negative 19, but it means one unit. And then the other thing I would just point out here is that this particular contract, let me turn this down so you don't have to listen to my, there we go. Thanks, guys. New Hope anymore. There we go. But just one other note here, each of these custom contracts is automatically created as objects are published in so that these functions that, for example, allow us to do things like setting token credits per ad are all properties of the content directly in the platform. All right, I realize I've gone well over my time, so I just wanted to wrap up, say that this is some work in progress, and we're very excited about it. If you guys have any questions, feel free to see me afterwards, and thank you for your time.